All right, y'all, another lesson today. Today we're talking about differentiability and continuity a little bit. So we talked about continuity last unit, and today we're going to talk about differentiability, which goes hand in hand with continuity. Okay, so I guess I'll just read the top. It says, in this lesson, we're going to investigate the relationship between continuity and differentiability. Our focus will be to determine when a function fails to have a derivative. Okay, a function that is differentiable at a point is also locally linear at that point. Basically, that tells us that in order for a function to be differentiable, it must be continuous and smooth at that point. Remember, when we say a function is differentiable, oh, this part's important. When we say a function is differentiable, this means that all over the place. This means that the derivative exists or that you're able to take the derivative. Okay, so today when we're trying to find out, is the function differentiable? That just means, can I take the derivative or does the derivative exist? So on Monday, last time we had our lesson, I drew some vertical tangent lines for you guys here, or there were some vertical tangent lines, or there was a cusp where we couldn't even draw a tangent line. So all of these situations on B, on C, and on D, the derivative fails to exist at that point. So here at C, at that point B, the cusp, I cannot take the derivative there. The derivative does not exist. It's non-differentiable. Same thing here on example C. At that point B, where there's the vertical tangent line, the slope is undefined. The derivative is undefined. It's non-differentiable. Same thing on part D. Right here at point A, I have the vertical tangent line, the slope is undefined, the derivative is undefined, it's non-differentiable. Okay, so this is what we're going to be talking about today. Right here, they give us the definition of differentiability at a point. A function is differentiable at a point, they're calling it C, if and only if. It says the limit as x approaches C from the left for f of x minus f of C all over x minus C needs to equal the limit as x approaches C from the right for f of x minus f of C, or all over x minus C. So hopefully this function looks familiar to you. This is the definition of the derivative, right? So they're saying that the derivative from the left needs to equal the derivative from the right. And we know that derivative is the same thing as slope. So they're saying the slope from the left needs to equal the slope from the right. Okay, so let's explore this definition a little more in this first example. Okay, now one of the most popular times a function will be non-differentiable is when we have an absolute value function. A function like this might show up on Friday's quiz. Who knows? I don't know, not me, not like I write the quiz or anything. All of these absolute value functions have a cusp or that sharp turn. And we know that at a cusp, the derivative does not exist. Okay, here's a little bit why. So part A is asking, what is the derivative as x approaches 1 from the left? Or another way to think of it as, what's the slope from the left of 1? Okay, so I've got this rise over run situation. I've got a slope of -1. Okay, and then on the right, same sort of thing, rise over run. This time I've got a slope of +1. Okay, so notice how they don't agree. A little frowny face there. Okay, so first thing they want to know is the function continuous at x equals 1? Well, yeah, it's continuous. There's not a hole. There's not a jump discontinuity. There's not an asymptote. Yes, it's continuous. But is it differentiable at x equals 1? No, it is not. The derivative, I should say f prime of x, as x approaches 1 from the left, is not the same as the derivative as x approaches 1 from the right. Okay, so even though my function is continuous here, it is not differentiable. Okay, important distinction there. It's continuous. I can trace the function. Go away. I can trace the function without lifting my pencil. No issue there, but I cannot take the derivative at x equals 1 because there's that cusp there. Okay, and I know this is going to happen anytime I have an absolute value function. Wherever the inside of my absolute value equals 0, that's where the cusp is going to occur. Okay, so this is our first example. Okay, absolute value functions will have a non-differentiable point. Okay, next example, we saw a picture, a graph that kind of looked like this on Monday's lesson when we were drawing in the tangent lines. It says, given the graph f of x equals the cube root of x, use the alternate form of the derivative to show that the function has a vertical tangent line at x equals 0. Okay, so they're wanting us to use this alternate form of the derivative. So I'm going to do the limit as x approaches 0. That's the point of interest here. Instead of f of x, I'll just write the function cube root of x minus, now I'm going to plug in 0 to my function, cube root of 0, all over x minus, again, my point of interest, 0. Okay, so I can clean this up a little bit. This is the limit as x approaches 0. I've got the cube root of x over x. Now, if I try and plug in 0 right now, I'm getting 0 over 0. Oh no, that does not mean straight away that it doesn't exist. That means that I can try and, you know, cancel some stuff and do some algebra skills. Okay, so I can rewrite my cube root of x to say x to the 1/3 power. That's the same thing. And my x on bottom has a secret exponent there of 1. Okay, if I'm dividing numbers that have the same base but different exponents, what I can do is I can subtract those exponents. So 1/3 minus 1 is negative 2/3. Again, I can rewrite this with a positive exponent as 1 over x to the 2/3. Okay, now if I'm plugging in 0, I'm not getting 0 over 0. I'm getting 1 over 0. Okay, so this is a viable reason to say that the derivative does not exist. F prime of 0 does not exist. Okay, I've got that vertical tangent line there. The derivative does not exist. It's non-differentiable at 0. Okay, so far we've talked about 2 different examples where a function could be non-differentiable. At a cusp, that sharp turning point, and wherever I have the vertical tangent line. Okay, when my definition of derivative gives me a number over 0. All right, last sort of situation where a function could be non-differentiable. Right here, they gave us the graph of f of x equals 1 over x plus 2 squared, and they even gave us the picture. Okay, it says describe the derivative of f as x approaches negative 2 from the left and negative 2 from the right. Okay, so first I'm going to find f prime of x as x approaches negative 2 from the left. Okay, so remember f prime of x, the derivative, that's the same as the slope. So as I'm getting closer, I want to see what kind of slope do I have here. Okay, it's kind of hard to find 2 points to find the slope of, but even though I can't find the exact slope, I know that my function is increasing, right? I'm going up, up, up. So I don't know the slope, but I'm going to say it's positive. Okay, as I approach negative 2, my slope is getting bigger and bigger and bigger and bigger and bigger and bigger. Okay, now as I approach, so my derivative as x approaches negative 2 from the right. So over here on the right, my function is decreasing this time. Originally I was increasing, now I'm decreasing. Okay, a lot of people are like, but I'm going up, I'm approaching that asymptote. Remember when we talk about slope, it's the rise over the run. So maybe you saw Slope Dude when you were back in Algebra 1. If you haven't seen Slope Dude, you probably don't know what I'm talking about. Go to YouTube, search Slope Dude and watch the video. But Slope Dude, he's skiing on that mountain, right? So from the left of 2, he would be going up the mountain, up, 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 positive slope. After negative 2, he's going down the mountain. He says, nice, negative slope. Okay, hopefully y'all have seen Slope Dude. If not, that makes no sense. Okay, go watch the Slope Dude video. Okay, so on the right side of negative 2, I have negative slope there. Okay, I'm decreasing. Okay, so I described what's happening from left and right. Hopefully you can see that these two do not agree. So I'm going to say f prime of negative 2 does not exist. At negative 2, my function is non-differentiable. Okay, we can prove that again right here on part B. This time they gave me the function of the derivative, f prime of x is negative 2 over x plus 2 cubed. Okay, there might be a question like this on Friday's quiz as well, where I give you the actual function of the derivative and I say, what is the derivative at x equals whatever? All you got to do is take the value of interest and plug it into your derivative formula. So -2 over -2 plus 2 cubed, I'm getting -2 over 0. So that does not exist. The function is non-differentiable here. Okay, so three main types of times we saw when a function was non-differentiable. The first thing we saw was that sharp corner or the cusp. Okay, absolute value functions. Then on example 2, we saw a vertical tangent line. The slope was undefined at that point. Okay, and what we just did, example 3, the function was discontinuous there. I had that vertical asymptote. Okay, now this is a really important part because this whole lesson, it says differentiability and continuity. We're investigating the relationship between differentiability and continuity. That brings me to this next point here. It says differentiability implies continuity. If f is differentiable at a point, then it must be continuous at the point. If a function is differentiable, then it is continuous. Differentiability implies continuity. Okay, all differentiable functions are continuous. It is possible for a function to be continuous but not differentiable. Continuity does not imply differentiability. For example, on the first two examples, both of these functions were continuous. Just because a function is continuous doesn't mean it's automatically differentiable. But if a function is differentiable, yes, that means it has to absolutely be continuous. If it's not continuous, no way it's going to be differentiable. Okay, so if you want to know if a function is differentiable, first ask yourself, is it continuous? If it's not, no way it's differentiable. If it is continuous, you got to do a little more work. It still might not be, but it could be differentiable. Okay, so down here, they want us to write the contrapositive of this statement here. So a little flashback moment to geometry. Okay, so they've told us something. They said, if a function is differentiable at a point, then the function is continuous at that point. This is true. If it's differentiable, it's got to be continuous. When we write the contrapositive, that will also be true. Okay, contrapositive is when you switch the hypothesis and the conclusion and you negate them as well. Okay, so this would be the contrapositive. If a function, I'm going to put that last part first and I'm going to negate it, is not continuous at x equals c. Then, now I'm going to state the first part, but negate it. The function is not differentiable at x equals c. Okay, so both of these statements are true. If it's differentiable, then for sure it's continuous. If it's not continuous, then for sure it's not differentiable. Okay, this is kind of similar to the idea that all squares are rectangles, but not all rectangles are squares. Okay, so if you've got a square, it's for sure a rectangle, you're good to go. But if you've got a rectangle, it might be a square, it might not be. You got to do a little more work to find out. Same thing here. If it's continuous, it could be differentiable. If it's not continuous, it's not differentiable. Okay, so important thing to know there. Sorry. Okay. Describe the x values at which the function is differentiable. We've got g of x equals the absolute value of x squared minus 5. Okay. Again, anytime you're seeing an absolute value function, you know that it's going to have that cusp, that sharp turning point. Okay. So, if you want to know where the sharp turning point is, what you can do is you can take the inside of your absolute value function and set it equal to 0, okay, and solve for x. So here x squared equals 5 and x equals plus or minus the square root of 5. This is where those sharp turns are going to occur. This is where the function, where g of x is not differentiable. Okay, but they asked, where is it differentiable? Okay, so it's differentiable everywhere else. So from negative infinity all the way to negative square root of 5. Okay, then at negative square root of 5, I'm good to go all the way until positive square root of 5. And after that, I'm good to go for the rest of the function. Alrighty. Okay, so I really like this example here. On the day, you know, we missed yesterday because of the storm. So originally this week, I was going to have a day where we worked with piecewise functions. We were going to do an FRQ with continuity and differentiability, because those are really popular FRQ questions they ask. I'm still gonna try and fit that in maybe next week, but I really like this example because it kind of picks up with a little bit what we missed from practicing with that FRQ. Okay, so here on this one, it says show algebraically using the alternate form of the derivative why g of x is not differentiable at x equals 1. And I've got this piecewise function. So it says when x is less than or equal to 1, we're using the function x squared. Okay, so it's going to look something like this, right? I've got that parabola there. And then when x is greater than 1, we're using the function y equals x. So it looks something like this. Okay, so here is my piecewise function, and they want to know, am I differentiable at x equals 1? Okay, well, first things first, it looks continuous. Okay, so there's a chance that my function could be differentiable, but we got to do some work to find out. Remember, in order for a function to be differentiable, the slope from the left or the derivative from the left must equal the slope from the right or the derivative from the right. Okay, so that's exactly what we're going to do here. They said use the alternate form of the derivative. Okay, so first I'll do the limit as x approaches 1 from the left. Alternate form of the derivative is the limit as x approaches c, f of x minus f of c all over x minus c. Okay, so since I'm doing from the left, I'm going to choose this top part of my piecewise function. My function is x squared. Okay, and then for f of c, I'm going to plug 1 into x squared, so 1 squared all over x minus my function, 1. Okay, so right now, if I try and plug 1 into this limit, I'm going to get 0 over 0. That does not mean it doesn't exist. That means I can like factor, cancel some stuff out. This is the limit as x approaches 1 from the left. I've got x plus 1, x minus 1 on top, all over x minus 1. So that cancels. And now I can plug in 1 plus 1 is 2. Okay, so my derivative from the left is 2. Let's check the derivative from the right. The limit as x approaches 1 from the right. Okay, I'm still using this alternate form of the derivative, but this time I'm going to use the bottom part of my piecewise function. My function is x. I'll plug in 1. And on bottom, x minus, my point of interest is 1. Okay, so if I plug in 1 here, I'm still going to get 0 over 0, but x minus 1 can cancel with x minus 1. And I'm left with not 0, I'm left with 1. So the limit as x approaches anything for 1 is 1. Okay, so now I can see, does my limit from the left agree with my limit from the right? No, it does not. Okay, so g of x is not differentiable at x equals 1 because the limit as x approaches 1 from the left for, oh, not f, g. I guess I should write g of x minus g of c all over x minus c does not equal the limit as x approaches 1 from the right, g of x minus g of c all over x minus c. Okay, again, the two slopes do not agree. Okie doke. So at this point, I was showing the class how to do a derivative in the calculator. Give me 1 second to pause and I'll see if I can pull up a calculator on my computer and share my screen. All right, hopefully now you are seeing my calculator on the screen. Okay, so I'm going to show you guys how to find a derivative on one of our TI Nspire calculators. Okay, so first thing I'm going to do is make sure that I'm in a regular like Scratchpad calculating screen. Okay, and what I'm going to do to find the derivative is I'm going to start by hitting menu. And all these options here come up. You can probably guess which one we're going to pick. I'll give you a hint. It's the name of the course, Calculus number 4. Okay, and once we're there, what we're trying to do is we're trying to find the derivative at a point. Okay, so this is the screen that's going to come up. Now, I have my notes page still up here on my iPad. Okay, so example number 8 was asking us to use the calculator to find the derivative of x squared minus 5x plus 6 at x equals -3. Okay, so x is going to be our variable here, and they want me to know, or they want to know first, where am I finding the derivative at -3? Hit enter. Okay, now this is going to come up on my Scratchpad. This says d dx, so I'm taking the derivative of, and this is where I'm supposed to put in my function. So the function they wanted us to do was x squared minus 5x plus 6. Okay, so the derivative of my function, and then this last part says at x equals -3. Hit enter, and you've got your answer. The answer here is -11. Okay, so f prime of -3 equals -11. Okie doke. And that was the end of today's notes. Okay, the last page from the notes was for you to complete for homework. So if you have any questions on that, let me know. Otherwise, I will see you guys later. So have a good one. Oh, I didn't stop the recording. Okay, bye.